Hello and welcome again to the lectures on state space approach to control system analysis and design. We are learning in this week the control design via desired closed loop response. In the previous part of the lecture, we got introduced to the concept of state and output feedback, and we did the control design using state feedback. We saw that arbitrary pole placement can be achieved via state feedback, while output feedback was seen to have limitations. We continue, and here the objective of the lesson is to learn the properties of state feedback, and also we will see the pole placement for uncontrollable but stabilizable systems. So first we look at the properties of the state feedback, and we begin with the companion form description of the system dynamics. The system is x dot equal to ax plus bu along with the output equation y equal to cx. In this, A is given in the companion form, and corresponding B matrix has unity only at the last element. C matrix has non-zero entries here, 1 here and then 0 thereafter. So B1 to Bm, before that 1, and rest all 0, m is less than n. Generally this is the situations. So with the help of this description, in which A, B and C are given like this, we will look at the properties of state feedback. What are the various properties of the state feedback? And we will take a classical approach, means we will try to show in terms of the transfer function. So the transfer function of that state space system, the system described by state space, is this. It is nth degree polynomial in the denominator and mth degree polynomial in the numerator. And as we said, m is generally less than n, and we are assuming that all the various a's and b's are positive quantities. Now with the state feedback, the closed loop transfer function of the system becomes this. We have seen otherwise also. We saw in the previous part of the lectures that when the system matrix is in companion form, with the state feedback given to this, the entries in this row change, and there we get, for example, an minus kn, an minus 1 minus k2 and so on. So if we take the transfer function, then those coefficients will come in the denominator, which will be this. So coefficient to Sn minus 1 is Kn plus A1. Coefficient of Sn minus 2 is Kn minus 1 plus A2 and so on. Coefficient of S is K2 plus An minus 1, and the constant coefficient is K1 plus An, the coefficient of S0. This is what the transfer function becomes. This is the closed loop transfer function, and I had emphasized it earlier. Once again, with the help of this, we can see that all the various coefficients in the denominator, they contain the gains k1, k2, etc. And that means that all the coefficients can be adjusted, can be altered by appropriate choice of the various gains K1, K2, etc. And that means the first property we get, it was told earlier, but here we once again we capture this point, that state feedback is capable of altering all the coefficients of the characteristic polynomial or all the pole locations. Arbitrarily it can change. That is one of the properties. Other properties we investigate based on the steady state error analysis as was done in the conventional approach. So what we do is we look at the response of the system at t tending to infinity by giving step input and ramp input. First we consider the step input. Here that RT will be R0. The input to the system will be R0, which is for t greater than 0 it is R0, and for t equal to 0 and before that it is 0. And its Laplace transform is of course R0 by S. If this input is given, and because this is the output is transfer function multiplied by the Laplace transform of input, so we get this expression for Ys. And so the steady state value of yt t tending to infinity, yt t tending to infinity will be given by limit s tending to 0 s ys. This is the final value theorem. And when we do this substitution here, we get that when steady state is achieved, the steady state value of y is this. And if this has to be 1, if the steady state error has to be 0, then yt has to be r0, and that means that this has to be equal to 1, which is written here. Bm by k1 plus an has to be 1, and that means k1 has to be the difference of bm. Bm is here the constant term in the numerator of the transfer function of the system, closed loop transfer function. So k1 has to be bm minus an. An is the constant term in the characteristic polynomial of the open loop system. So if k1 is equal to this difference, then there will be 0 steady state error for step input. Means that we can select the state feedback gain k1 based upon achieving 0 error for step input. That can be done. So state feedback is capable of achieving 0 steady state error for step input. We proceed ahead and we see for the ramp input. For the case of ramp input, as we know, ramp input is described by this. RT is a slope times t. RT is like this, and this slope is R1, we are assuming. This is how the ramp input behaves versus t. So the Laplace transform, this is Rs, which is R1 by S square. When this input is given, and of course Es, the error, Laplace transform of error will be Laplace transform of output minus the Laplace transform of the reference input, and so Es by Rs will be Ys by Rs minus 1. This is the transfer function of the system, and so Es will be this into Rs. So we calculate that Es will be this. If we do the manipulations with the help of this, we will get this. And in that based upon the step input, we have designed that Bm will be equal to K1 minus An. So this cancels with this. And at t tending to infinity, the steady state value of Et will be obtained as limit s tending to 0 SES. This one has cancelled, we saw. And if we do SES, then we get this relation. Bm minus 1 minus K2 plus An minus 1 into R1 divided by Bm should be 0, or that will give this expression, and from that we get K2. So if we choose K2 as difference of Bm minus 1 and An minus 1, Bm minus 1 is the coefficient in the numerator and An minus 1 is the coefficient in the denominator of the open loop system. So we get K2 like this, then the steady state value of error will be 0 for ramp input, and that means that by pole placement and appropriate selection of the gain K2, we can force the steady state error to ramp input to 0. Similarly, we can force the steady state error to parabolic input to 0 by selection of K3 like this. And in this manner, based upon the steady state error analysis to step, ramp, parabolic input and other higher order inputs, we can make all the various steady state errors 0. So we get to these properties of state feedback. First thing is that poles can be placed arbitrarily with the natural restriction of complex poles appearing as complex conjugate pair. Steady state error to step, ramp, parabolic and other higher order inputs can be made 0. This is the property of the state feedback. This cannot be achieved generally by output feedback. State bit feedback, I am again emphasizing, is much more powerful compared to the output feedback. Now we come to the second topic of this part of the lecture, the pole placement for uncontrollable but stabilizable systems. If a system is not fully controllable, or if the system is uncontrollable, then it is only possible to arbitrarily place the controllable eigenvalues, controllable poles of the system, and uncontrollable eigenvalues will remain unchanged. So we have seen while learning the controllability through Gilbert's criterion or through Haughton's criterion, it is possible to know that which eigenvalues are controllable and which eigenvalues are uncontrollable. So in case of an uncontrollable system, we can know the uncontrollable eigenvalues and the controllable eigenvalues, and only the controllable eigenvalues or the controllable poles will be possible to be placed. We have also seen that if we have linear time invariant system described by this state equation, whose controllability subspace is of lower dimension n1 than n, then it can be transformed into a controllable system and an uncontrollable system. The order of controllable system will be n1 and the order of the uncontrollable subsystem will be n2, which is difference of system order and the order of the controllable subsystem. So the uncontrollable system, a system which is not fully controllable, can be decomposed into a controllable subsystem and into an uncontrollable subsystem. How it is possible to do, we have seen earlier and we recall. So what we do, the controllability matrix we pick up the linear independent columns of the controllability matrix as T1, and the remaining columns T2 we arbitrarily select, and we get the transformation matrix T. And through this T we can manipulate the given system to break it into, to decompose it into controllable subsystem characterized by this, and uncontrollable system characterized by this. So the ACC bar, BC bar characterize the controllable subsystem, and AUU bar and 0 here. So AUU bar, autonomous system, is that uncontrollable system. So we get the decomposed system. The order of the controllable subsystem is N1 and the order of uncontrollable subsystem is N2. Now we design the controller only for the controllable part. So say that controller is KCZC. This is the controllable part. So for this we design this controller, and the objective is to get a desired characteristic equation which is of order N1. It is not of order N. N is the system order, N1 is order of the controllability, controllable part of the system, or controllable subsystem, or the controllability index. So we can design the controller to get a characteristic polynomial only for the controllable subsystem, and it is a lower order polynomial than N. Its order is only N1. The uncontrollable part controller cannot be designed, so we take its gain as 0. The input for the uncontrollable system is 0 times the states of the uncontrollable system that we take, meaning that the characteristic polynomial of the uncontrollable system remains unaltered as this. This is the characteristic polynomial of the uncontrollable subsystem, and this is the characteristic polynomial of the controllable subsystem, which is achieved through this feedback of only the states which are controllable, the ZC part. And next what we have to do is we have to combine to obtain the control for the full system, which is KC, the one designed for the controllable subsystem, and 0, which is assumed for the uncontrollable subsystem. And so the input is given this as the K matrix and this as the Z matrix. This KZ, KC ZC plus 0 ZU, KC ZC plus 0 times ZU. This is the controller for the full system. KC has been designed. And now the controller for the original system will be obtained, because this Z is T inverse X. So this input for the original system will be the gain of the system after decomposition multiplied by the T inverse. And so we get the, this is the gain matrix KC 0 T inverse. This is the gain matrix for the original subsystem. And with that, the characteristic polynomial of the closed loop system will be the product of the characteristic polynomial of the closed loop system for the controllable subsystem and the characteristic polynomial of the uncontrollable system, which is this. This will be the characteristic polynomial of the closed loop system. Means only the those characteristic polynomials can be achieved which are factored like this, in which this has to be a separable factor. Then the pole placements for DCC will be achievable in this case. And of course, the closed loop system design will be stable only if AB is stabilizable, meaning that only if the roots of this polynomial, the uncontrollable polynomial, are already in the left half S-plane, then only the closed loop system designed through this DCC, the desired characteristic polynomial of the controllable subsystem, will be stable. Only then the closed loop system will be stable. We see with the help of this example, we have this uncontrollable system, this has A matrix, this has B matrix. Now it is easy to see that this uncontrollable part is separated, corresponding element in B matrix is 0, and that is how it is uncontrollable. This is the controllable part which is in diagonal form, and the entries in B corresponding to both the rows, this row and this row, they are non-zero. So this system is uncontrollable because of that, and this part is the controllable part and this part is the uncontrollable part. Now we have to design the control for this system. We see that uncontrollable system which is characterized by these or this is stable because the eigenvalue is -3, the real part is negative. So we can design a controller for the controllable subsystem, and we can achieve some performance specifications and of course the stability, because uncontrolled part is stable. So we consider this controllable subsystem, and we see that this is its characteristic polynomial, the characteristic polynomial of the open loop controllable subsystem. We want to place its poles. At -1 and -2, and we want to achieve this characteristic equation of the closed loop controllable subsystem. This DCC open loop poles are here, 1 and 2, indicating instability. So we want to stabilize, and probably this one will give a overdamped response which is acceptable for our purpose. So we do the design. Of course we don't do transformation to companion form, we proceed directly. That will be little cumbersome, but this is only a second order system, so it can be done. So this is the A, that controllable subsystem, and this is the product BK. B is B is 1 1 here, so 1 1 into KK, this 1 1 into K, K1 K2, that gives this product. So K1 K2 K1 K2, and when subtracted we get this closed loop system matrix corresponding to the controllable subsystem. This will be the A minus BK, and its characteristic equation, characteristic polynomial will be obtained like this. Determinant of A minus BK with this here, we will get this, and we want the desired characteristic polynomial to be this. So we compare the coefficients of different powers of S. So we get K1 plus K2 plus 3 equal to 3, and 2K1 plus K2 plus 2 equal to 2. So we get these equations, and we solve these equations to get K1 and K2, and so we have the gain matrix. This is the gain matrix for the controllable part, and this is the gain matrix for the uncontrollable part. So we assemble the K for the transformed system, and in this case transformed system is same as the original system. So we get the K and we get the corresponding pole locations as -1, -2 and -3. We summarize this part of the lecture also. We have seen that state feedback is capable of achieving arbitrary pole placement, and it may also eliminate steady state errors if the control gains are chosen so as to eliminate the errors. And of course the numerator or the zeros of the system also should be there. There must be some finite zeros in the system. So steady state errors can be eliminated. We also saw that if the system is not fully controllable, still state feedback control could be designed for the controllable subsystem, and the overall performance of the closed loop system may be acceptable. Of course, it is not possible to place all the poles, only the poles of the controllable subsystem could be placed, but the overall response, because it is stable, so may be close to desired, although not arbitrary pole placement may be possible. So using that decomposition, we could design the state feedback gains for placing the poles for uncontrollable but stabilizable system also. So with that we conclude this part of the lecture also. Thank you very much.